this Chem help video, we're going to look at the concept of the corrosion of iron as part of the Year 12 Chem course. This is an interesting topic. It's new to the WACE course. It was a huge part of the TE course back in the day and was really scary, and everyone used to panic about it. And then in the early days of the new course, it was like that. And then a few years ago, when we introduced the Unit 3 and 4 courses, it was dropped from the curriculum, but still taught by some people who are trying to emphasize the importance of the oxidation reduction processes that are going on. But it is a really useful tool for that, so it's made its way back into the course. So this video is to try and demystify that for you, make it a little bit less scary, because it is actually a very simple thing that we just like to go through with you. So hopefully it makes some sense. Okay, so let's look at this corrosion process. Now, corrosion needs to be seen as part or as extension of the redox topic. It's not a separate topic. First and foremost, we need to remember that corrosion is simply an electrochemical process, the same as all of the other electrochemical processes that you've looked at in this topic. You've looked at galvanic cells, you've looked at spontaneous redox, you've looked at displacement reactions, you've looked at a whole different range of redox processes, and corrosion is just another one of those. As with any redox process, you have a place where oxidation occurs and electrons are lost from a metal. We have a place where reduction occurs, and a non-metal in this case is gaining electrons, but it's the same as every other redox process. We have a place where oxidation occurs, and of course a place where reduction occurs. As all the other processes, electrons travel from the anode to cathode. Now in a cell that you would have set up, it travels through the wire, the copper connecting wire. Well, in this case, it travels through the metal, just like it would in a normal electrochemical cell. Cations always go to the side of reduction, or the cathode, so cations to cathode, and of course anions go to the anode, the side of oxidation. So nothing there is new. Everything on the screen at the moment is something that you would know if you drew a simple electrochemical cell. All electrochemical cells have a salt bridge, and that's where the role of the water comes into it, part of the role of the water, I should clarify that, but that's the salt bridge. So again, electrochemical cells have a salt bridge. Okay, so let's have a look at a basic corrosion scenario. First of all, we have solid iron. There are some other metals that corrode, of course, but we're going to focus specifically on the corrosion of iron. So we're looking at, you need solid iron. You also need a water droplet, and you need oxygen in the atmosphere. Those three things are absolutely essential if we're going to have corrosion, and we'll talk about that a little bit later on. Now, what happens? Well, first of all, the oxygen and the water, now both are required. The oxygen has a role and the water has a role. They gain electrons, and they get the electrons from the iron, and they form hydroxide ions. The iron is oxidized into iron 2+ ions, giving up 2 electrons. Now you see that we've got one equation giving up 2 electrons and one equation receiving 4 electrons, so of course that means you've got to do some balancing when you combine them to cancel out those electrons. Now this oxidation point happens as far away from the oxygen source as possible. So if you've got a droplet or a circle of water, it's going to happen right at the center. And this is really interesting because like if you have some screws or nails in a piece of wood, often from the outside, if you look at the nail or screw, it might not appear corroded, but if you pull the nail out of the wood that's been there for a while, often the tip of the nail will be quite heavily rusted or corroded. That's because the tip of the nail is as far away from the oxygen source as possible, and that's quite a common thing. And that makes an interesting phenomenon happen that I'll show you in a slide or two. So what happens is we've got a cathodic site, so that's where the electrons are gained, and we have an anodic site, which is where the electrons are lost. So that's nothing new there. In every other redox example we've looked at, oxidation, loss of electrons, reduction, gain of electrons. And we've got our 3 components there. Iron, oxygen, and water. All very, very important. Now, in a salt bridge, ions move in the salt bridge or in the electrolytes, and the same thing happens in this scenario. The water droplet acts as the electrolyte, and the cations go to the cathode and the anions go to the anode. So that means that the Fe2+ goes towards the cathodic site, so the edge of the droplet, and the hydroxide ions move to the center of the droplet. And the electrons travel through the wire, alright? And in this case, the wire is the metal itself. and electrons, as always, travel from anode to cathode. Now what happens here is that we have our production of our two different types of iron. So our cathode produces the hydroxides and our anodes produces the iron too, and they move in the solution like this. And when they move in the solution like that, eventually the iron 2 moves to the edge, the hydroxide moves to the center, and they meet in the center of those 2 points. And that forms some iron 2 hydroxide, and that will form a little blob or crater that you can see there. Now at the center here, what we've got is we end up forming a bit of a divot. Now what's going here is this is where the iron 2 has turned, the iron has turned into iron 2 ions, leaving space behind, and the water fills that. So the iron 2 moves this way, hydroxide moves this way, and it forms this iron 2 hydroxide in the middle between the two places where it started originally. Again, that's where the cathodic side is, that's where the anodic side is. And over time, what we end up with is a scenario that looks a little bit like this. Okay, so we have a big crater being produced in the center with a little lump. Now, it looks like two separate lumps, right? But what it would be like a donut. All right, if you looked at it from the top, what you have is the center is like a depression, and then you get a ring of the iron 2 hydroxide around the outside. Now, what that means is that we call that cratering. All right, so when the water dries out, the iron 2 hydroxide turns into iron 3, and the iron 3 then partially dehydrates into what we call rust. So a rusted material. Now if you look up really closely at a rusted material, it looks like little tiny pimples or divots, little craters, and that's called pitting corrosion. Now the pitting corrosion is it actually eats into the metal and forms this depression and then a little lump around the outside, and you can feel that, and you look at a piece of metal that's rusted and you run your hand over it and it feels rough, and then you sand it back, and it takes quite a lot of time to get rid of not only the rust but then to get down to that, get rid of that pitting as well, and you can feel that quite easily on anything that's rusted. It's very, very characteristic. Now, preventing corrosion causes a lot of confusion for people, but if we just look at this simple triangle example, it might make a bit more sense. For rusting to occur, you have to have the iron that can be oxidized and the water and the oxygen that can be reduced. They're both required. So we have this triangle: iron, oxygen, and water. Now, if we don't have any one of those three things, we simply do not have corrosion. It's like the old fire triangle, if you know that one. Fire triangle: fuel and oxygen and heat. Without one of those three things, you can't have fire. Well, for corrosion, it's the same. Without iron, oxygen, or water, you can't have any corrosion. So what's that mean? Right. So if you have a piece of iron and it rusts, and you're trying to build something, well, one option you might do is don't use iron, use a different metal. So you take the iron out, use a different metal that doesn't corrode as easily, problem solved, doesn't rust, right? Change the nature of the iron. So we have, for example, steel, and we have stainless steel. So stainless steel has some chromium in it. Change the nature of the iron, we don't get corrosion. Then we've got some simpler methods like remove oxygen. So if you're in a vacuum of space, for example, a piece of metal won't rust. There's no oxygen. So if we can somehow remove the oxygen from the system, then we do not get corrosion. And that's why things like shipwrecks at very, very deep depths don't rust as fast. Because at deep depths, there isn't very much dissolved oxygen in the seawater. So though you've got an iron ship and clearly lots of water in the sea, we don't have a lot of oxygen. So not a lot of oxygen, plus the cold temperatures, slows the reaction right down, because limited oxygen means you simply can't corrode. Okay? Shallower depths, where there's a lot more oxygen dissolved in the water, then we have faster rate of corrosion. Or we can try and remove the water. Now we can remove the water from really simple things by keeping something dry, reducing the humidity around the water, or we can use simple barrier methods as well to stop water or oxygen getting to the iron. So for example, plastic coating something might stop the iron from corroding, stops oxygen and water getting there. But we've got a couple of other methods as well that we can use, and here are some of those summarized really briefly on this slide. So we can modify the environment, take away the oxygen, take away the water. We can modify the iron. We can alloy it to make it less likely to corrode. we can cathodically protect it. Now what that means, and I'll get you to look this up, is that you apply a voltage to the metal. And what that means is that you apply electrons to the metal. Now, iron can't lose electrons if you're applying electrons to it. Alright, so to be oxidized, it's got to be the most substance that's easily losing electrons. But if you're applying electrons through a voltage, it can't corrode. So we use this for bridges and things like this. So if you've got a bridge sitting in a river, it'll corrode. So what we do is we provide a very low voltage to it, and we make the bridge the cathode of an electrolytic cell. Now if it's the cathode is where reduction occurs. We can't oxidize something that's being the site of reduction. Alright? So that's how we protect it. We can use protective metal coatings. We can coat with a better metal. So like for example chrome plating motorcycle parts. Chrome goes over the top of the metal and not only does it look nice and shiny, but it protects it. We call that a noble coating. We could plate it with gold or silver or something like that. The problem with the metal coatings like that is that noble coatings, if they get scratched, it exposes the metal underneath and it rusts faster underneath. So one of the things about in the old days when they used to have tin cans all the time, so a tin can was like a steel can coated in actual tin. If you wanted to dispose of those by burial those days, recycling wasn't big, what they would want you to do was to crush the can. And what the crushing of the can would do would crack the tin layer and enable the iron to corrode. And in fact, when you crack the noble coating, the actual underlayer corrodes faster, because when you have two different metals in contact, the more reactive metal will corrode faster. So noble metal is really good, but you can't scratch it. And the same thing happens like if you have a chrome bumper on a car and you have a dent in it. Once it's dented and it's cracked the chrome, you're going to corrode faster. The other way we can have is we can have a sacrificial coating. So that's called galvanizing is an example of that, where we put zinc around the outside. Now that's again two metals in contact, but zinc is preferentially oxidized to the iron. So if that gets scratched, that's totally fine, because oxygen and water can still get to the iron, but the zinc corrodes first. So when you see those barriers down the freeway and they've got that sort of dull look about them, that's because they've been covered in zinc, and the zinc is corroding instead of the iron that they're covering. But you can scratch that just fine. So that's why you have that kind of coating on things like nails and screws. Obviously when you put them into the object that you're fixing, you'll scratch it, right? And that doesn't matter, because the scratch doesn't affect the corrosion of the iron, it only affects the corrosion of the zinc itself. And of course then you can have metallic, non-metallic protective coatings as well, so things like paint. Right, so that's why we're constantly painting ships. If we paint the ship, we stop the water and we stop the oxygen getting into contact with the iron. And if you prevent that, go back to our triangle model, then we've solved the problem. Same thing, that's the function of oil as well. Put oil over something, it doesn't rust. Why? Because the oil stops the water getting to the actual substance because of the difference in solubility between oil and water. Plastic coating, as I said, wrapping something in a film, all those things help prevent corrosion. So hopefully that's demystified that for you, because it's not supposed to be hugely complex. It's a simple electrochemical process. Site of oxidation, site of reduction, movement of ions, movement of electrons. We get a net reaction happening. That's corrosion. So hopefully that's just demystified that, and let me know through the comments if you have any questions. Okay, thanks very much.